What is a network protocol? Every time your phone loads a web page, sends an email, or downloads a file, something is making sure that communication actually works. That something is a network protocol. A network protocol is a set of rules and message formats that define how devices communicate with each other over a network. It covers how data is packaged, how devices identify each other, how errors get caught, and how information is retransmitted if something goes wrong. Because these rules are published as open internet standards, a laptop made by one company can talk to a server made by a completely different company without any confusion. Without protocols, every device would basically be speaking a different language, and the internet would be a very quiet place. There are thousands of protocols, each responsible for a specific piece of how the internet functions. Address resolution protocol. When two devices on the same local network want to communicate, they need more than just an IP address. They need a physical hardware address, called a MAC address, to actually deliver data at the local level. This is where the address resolution protocol comes in. When a device wants to send data to another device on the same network, it broadcasts a request to everyone on that network, essentially asking, who has this IP address? The device that owns that IP address replies with its MAC address. The first device now has what it needs and the communication can proceed. The address resolution protocol is completely automatic, happening invisibly in the background every time devices talk to each other locally. Without it, local network communication simply would not work. File transfer protocol. The file transfer protocol is exactly what it sounds like. It is a standard protocol used to transfer files between a client and a server, either over the internet or within a local network. It works on a client-server model where the client connects to the server and can upload or download files. The client sends commands like RETR, which stands for retrieve, to request a specific file, and the server responds by sending it. The file transfer protocol supports both anonymous access, where no credentials are needed, and authenticated access requiring a username and password. One important limitation is that it does not encrypt data during transfer, which makes it unsuitable for sending sensitive information in its basic form. For secure file transfers, upgraded versions like FTPS or SFTP are used instead, which add encryption on top. Simple Mail Transfer Protocol. The Simple Mail Transfer Protocol is the standard used for sending and relaying email messages between servers. When you hit send on an email, your email client, whether that is Outlook, Gmail, or anything else, connects to an SMTP server and hands off the message. The server then routes that email toward the recipient's mail server. The protocol works as a push system, meaning it pushes messages outward toward their destination. A basic SMTP exchange starts with the client sending a hello command and the server responding with a 250 code, which signals that it is ready to proceed. From there, the sender, recipient, and message body are all communicated in a structured sequence. Like the file transfer protocol, the Simple Mail Transfer Protocol does not include encryption in its base form, which is why the secure version, SMTPS, exists for protected email transmission. Hypertext Transfer Protocol and HTTPS. The Hypertext Transfer Protocol is the foundation of how data moves across the web. Every time you open a website, your browser sends an HTTP GET request to a web server asking for a specific page. The server responds with a 200 OK status and delivers the content, typically written in HTML, which stands for Hypertext Markup Language. This is the request and response cycle that powers every website you have ever visited. The problem with basic HTTP is that the data travels in plain text, meaning anyone intercepting the connection can read it. That is where HTTPS comes in. HTTPS is HTTP running inside an encrypted tunnel created by SSL or TLS protocols. SSL stands for Secure Sockets Layer, and TLS stands for Transport Layer Security, with TLS being the modern, more secure replacement. Together, they encrypt the data exchanged between your browser and the server, protecting it from eavesdropping and tampering. Domain name system. Humans are not great at remembering strings of numbers. Nobody types 142.250.74.78 into their browser to get to a website. Instead, we use domain names, and the domain name system is the protocol that makes that possible. It acts as the internet's phone book, translating human-readable domain names like www.youtube.com into the numerical IP addresses that computers actually use to locate each other. When you type a web address into your browser, your device first sends a query to a DNS server asking for the IP address that corresponds to that domain name. The DNS server looks it up and sends the address back. Your browser then uses that IP address to connect to the actual web server. This entire lookup process happens in milliseconds and is completely invisible to the user. Without the domain name system, navigating the internet would require memorizing the IP address of every single website you wanted to visit. Dynamic Host Configuration Protocol. Every device that connects to a network needs 4 things configured to function properly. It needs an IP address to identify itself, a subnet mask to understand the size of its local network, a default gateway, which is the router's IP address used to reach outside networks, and the IP address of a DNS server to resolve domain names. Configuring all of that manually on every device every time it connects to a new network would be a nightmare. The Dynamic Host Configuration Protocol solves this entirely. When a device joins a network, it sends out a DHCP discover message looking for a DHCP server. The server responds by automatically assigning all 4 of those required values to the device. This is exactly what happens every time your phone connects to a new Wi-Fi network without you touching a single setting. Secure Shell. The Secure Shell protocol is used to securely access and manage remote servers and devices over a network that may not be trusted. It creates an encrypted channel between a client and a remote machine, through which a user can run commands, transfer files, and perform administrative tasks as if they were sitting right in front of that machine. All data exchanged over a Secure Shell connection is encrypted, which means even if someone intercepts the traffic, they cannot read it. Authentication is handled either through a password or through cryptographic keys, which are essentially a matched pair of long encrypted strings that verify identity without sending a password at all. Secure Shell replaced an older protocol called Telnet, which we will get to shortly, and it remains the standard tool for remote server administration across the entire industry. Transmission Control Protocol and Internet Protocol, TCP and IP together form the foundational suite that underlies the majority of internet communication. The Internet Protocol handles addressing and routing. It is responsible for assigning IP addresses to devices and making sure that data packets are directed toward the correct destination across multiple networks. The Transmission Control Protocol handles reliability. Before sending data, it establishes a connection between the sender and receiver through a process called the 3-way handshake. It then breaks data into packets, sends them, confirms they all arrived, ensures they are reassembled in the correct order, and requests retransmission of anything that got lost. This combination makes TCP and IP the backbone of reliable internet communication. When you need data to arrive completely and correctly, like loading a web page or downloading a file, this is the protocol suite doing the work. Post Office Protocol 3 and Internet Message Access Protocol. While the Simple Mail Transfer Protocol handles sending emails, 2 other protocols handle the other side of the equation, which is retrieving emails from a mail server. POP3, which stands for Post Office Protocol version 3, downloads your emails from the server directly to your device and then typically removes them from the server. This means you can read your emails offline, but access from other devices becomes limited since the messages are only stored locally. IMAP, which stands for Internet Message Access Protocol, takes a different approach. It keeps your emails stored on the server and syncs them across all of your devices in real time. If you read a message on your phone, it shows as read on your laptop too. For anyone accessing their inbox from multiple devices, IMAP is the more practical option. User Datagram Protocol. Not all internet communication needs to be perfectly reliable. Sometimes speed matters more than accuracy. The User Datagram Protocol is built for exactly those situations. Unlike the Transmission Control Protocol, UDP does not establish a connection before sending data, does not confirm delivery, and does not guarantee that packets arrive in order. It simply fires data out and moves on. This makes it significantly faster and more efficient for applications where a small amount of data loss is acceptable, and waiting for retransmission would cause more problems than the lost data itself. Live video streaming, online gaming, and voice-over IP calls all use UDP because a slight drop in quality is far less disruptive than the delay caused by stopping to resend missing packets. It is not careless, it is just optimized for a completely different priority. Telnet. Telnet is one of the oldest remote access protocols, dating back to 1969. It allows a user to connect to and control a remote device over a network using a command line interface. The fundamental problem with Telnet is that it transmits everything in plain text, including usernames, passwords, and every command typed. There is no encryption whatsoever. This means anyone with access to the network traffic between the client and the remote machine can read the entire session without any effort. In today's environments, that is an unacceptable security risk. Telnet has been almost entirely replaced by the Secure Shell protocol, which does everything Telnet does, but with full encryption. Telnet still occasionally appears in legacy systems or controlled lab environments, but using it on any network with real security requirements is essentially volunteering your credentials to whoever is listening. Simple Network Management Protocol. The Simple Network Management Protocol is used by network administrators to monitor and manage network devices from a centralized location. It works on a client-server model where managed devices, such as routers, switches, and servers, run small software agents that collect performance data. A central system called the Network Management System queries these agents to retrieve information about device status, bandwidth usage, error rates, and other metrics. The agents can also be configured to send automatic alerts if something goes wrong without waiting to be asked. This allows administrators to catch problems early, track performance trends over time, and configure hardware remotely across an entire network from one place. Without something like the Simple Network Management Protocol, managing a large network would require physically visiting every single device to check its status. Internet Control Message Protocol. The Internet Control Message Protocol is not used to transfer data between applications. Its job is to report errors and provide diagnostic information about what is happening on the network. When a data packet cannot reach its destination, it is often an Internet Control Message Protocol message that comes back to the sender explaining what went wrong. Two of the most commonly used network diagnostic tools are built entirely on this protocol. The ping command uses it to test whether a remote device is reachable and measures how long the round trip takes. The traceroute command uses it to map the path that data takes across the network, showing every hop along the way and how long each leg of the journey takes. These tools are typically the first thing a network engineer reaches for when diagnosing a connectivity problem. Network Time Protocol. Accurate time synchronization across a network matters more than most people realize. Log files, security certificates, database transactions, and scheduled tasks all depend on devices agreeing on what time it is. If one server thinks it is 3 hours behind another, log entries become impossible to correlate, and certain security systems will outright reject connections from devices whose clocks are too far off. The Network Time Protocol solves this by allowing devices to synchronize their clocks with dedicated time servers, which in turn get their time from highly precise sources like atomic clocks. The protocol accounts for network delays to ensure the time received is as accurate as possible. It operates continuously in the background, making small adjustments to keep all devices on the network in sync. Routing Information Protocol and Open Shortest Path First. When data travels across the internet, it passes through multiple routers before reaching its destination. Routing protocols are what tell those routers how to make decisions about where to send data next. The Routing Information Protocol is one of the oldest and simplest routing protocols. It determines the best path by counting hops, meaning the number of routers data passes through to reach its destination. It chooses the path with the fewest hops. The main limitation is that it cannot handle networks with more than 15 hops, and it is slow to adapt when network conditions change. Open Shortest Path. First is a more advanced protocol that uses a cost-based metric considering factors like link speed rather than just hop count. It adapts faster to network changes and scales much better for large, complex networks, making it the preferred choice in most modern enterprise environments. That covers every major protocol powering the internet you use every single day. If you want to keep going with the hardware side of things, the next video breaks down every tier of RAM in detail. It is worth watching before your next upgrade decision.